Hi friends, so in this video we discuss AC and DC analysis of a small signal amplifier. In this video we just discuss DC analysis of a small signal amplifier. In next video we discuss about the AC analysis of a small signal amplifier. So we already discussed about the small signal amplifier. So this is the small signal amplifier. So this small signal amplifier is works both AC and DC signals. You can see. So here the DC is used for biasing purpose. DC is used for biasing purpose and AC is used for the amplification of a small signal. So here small signal is nothing but the message signal or information signal. Okay. So next you can see in this circuit both AC current and DC current is flow inside the small signal amplifier. The red line indicates the AC current. AC arrow indicates the red arrow indicates the AC current and green arrow indicates the DC current. Okay. So from this figure we can write the total current passing through the base junction is IB is equal to capital IB and small letter IB. So here IB is the total base current and this one is the DC current and this one is the AC current. Similarly, from the figure we can write collector current also. So this is the DC collector current and this one is the AC collector current. Okay. So DC equivalent circuit. Here we made two changes on the small signal amplifier. We get the DC equivalent circuit. The first change is for DC the coupling capacitors works as open circuit. So coupling capacitor means in this figure you can see C1 and here also there is a capacitor. So you can see in this circuit here and here. So these are the coupling capacitor. You know the working of the coupling capacitor. So this coupling capacitor for DC behaves as a open circuit. So that's why we neglect or we remove these capacitors. Next another point is the for DC assumes all AC sources to 0. So for DC assumes all AC sources to 0 or these AC sources can be connected to ground. So here there is a AC source here. Next. So this is the DC equivalent circuit. You can see. So in this circuit there is no AC source and there is no AC current flowing through the circuit. So there is a only present DC source and DC currents here and here. Okay, next DC load line. DC load line. So this load line can be represented in the output characteristics of the transistor. So here there is a relation between IC and VCE, collector current and collector emitter voltage for a zero signal, the absence of AC signal. So this is the output characteristics of a transistor. So there is a relation between VCE and IC. So this line indicates the DC load line. So from this figure we can show the relation between IC and VCE. So apply KVL on the apply KVL on the output portion of the DC equivalent circuit. So here, so VCC is equal to IC RC plus VCE. VCE is the voltage across the collector terminal and the emitter terminal, plus IE and RE. So this is the KVL, Kirchhoff voltage law, at the output portion of the DC equivalent circuit. So from the relation we have IC is nearly equal to IE. IE. So from this relation, so the equation becomes VCC is equal to IC RC plus VCE plus IC and RE. Then VCC is equal to IC times RC plus RE plus VCE. Then the relation between IC and VCE is IC is equal to VCC by RC plus RE minus VCE divided by RC plus RE. So this is the relation. So we have, there is a straight line equation, or IC is varied with linearly, means y is equal to, straight line equation, y is equal to mx plus c. So here, so this is the slope m and this is the y-intercept. So this y-intercept is constant, VCC is constant, RC plus RE is also constant. The slope is 1 divided by RC plus RE. So there is a negative slope, minus negative slope. So that's why we have this type of line, So this line indicates the negative slope. The slope is equal to m is equal to minus 1 divided by RC plus RE. So in this load line, so here we have IC is equal to 0. So on the x-axis, y-axis is equal to 0. So y-axis we take the collector current. So collector current at this point is 0. So the relation IC is equal to VCC by RC plus RE minus VCE divided by RC plus RE. So in this relation, so IC which is equal to 0, so then VCC is equal to VCE. Okay, so this is this point you can see VC is equal to VCC. So here it is comes. So this point is lie in the cutoff region. So this is the cutoff region. So next we talk about this point. So here, so this is the y-axis. On the y-axis, x-axis becomes 0. So here we take x-axis equal to VCE. So VCE is equal to 0. Then relation IC which is equal to VCC by RC plus RE minus 0, because here the VCE is equal to 0. So from this reason IC is equal to VCC by RC plus RE. You can see here IC is equal to VCC divided by RC. So here we have, so IC is equal to VCC by RC plus RE. So this graph taken for without RE, but here there is a RE present in this circuit. So IC is becomes VCC divided by RC plus RE. So this is the DC load line, means the transistor takes the probable values of the IC and VCE. So this makes the straight line. So here IC is where is in this straight line path. So this is about the DC equivalent circuit. So in this DC output characteristics of a transistor, we have three regions. So this is cutoff region. So this point is in saturation region and this is the active region. The transistor must have the Q point in the middle of the DC load line, and also this Q point is must be lie in the active region. So this is about the DC equivalent circuit. So in this DC equivalent circuit, we can study DC used for biasing purpose. So without DC, the transistor means small signal amplifier doesn't work. Next, DC provide proper operating point. DC provide proper operating point. Because of proper operating point, we get non-distorted wave, output wave. Okay, thank you for watching.